the graph was supposed to fall. Instead, it kept stretching outward, almost perfectly flat. That single line first appeared where astronomers expected gravity to begin losing its grip. Beyond the bright spiral arms of a galaxy, the stars should have slowed as their distance from the center increased. The equations had worked for planets around the sun. They had held up across generations of astronomy. There was every reason to believe galaxies would behave the same way. The only missing piece was a measurement that reached far enough into the darkness. On cold nights at Kitt Peak National Observatory, a large telescope carried an instrument unlike the photographic systems astronomers had relied on for decades. Kent Ford's image tube spectrograph could collect faint light from the outer edges of galaxies far more efficiently than older equipment. That mattered because the regions astronomers wanted to examine were also the dimmest. Glass photographic plates emerged from the observatory carrying thin spectral lines, physical records of light that had traveled millions of years before reaching Earth. At first glance, they looked ordinary, almost delicate. Their importance came not from their appearance, but from tiny shifts measured under a microscope. Back in the laboratory, Vera Rubin placed each plate beneath crosshairs capable of detecting movements measured in microns. One line after another was compared against known laboratory wavelengths. Those minute displacements revealed how fast gas and stars were moving through the Doppler effect. Numbers gradually filled handwritten notebooks. Nothing looked unusual. Only when those measurements became points on graph paper did the contradiction emerge. The expected curve never appeared. Instead of bending downward beyond the visible disk, the plotted velocities remained almost level. Stars far from the galactic center continued orbiting at nearly the same speed as stars much closer in. The farther the graph extended, the less it resembled the prediction everyone expected. Something seemed wrong. Wrong enough that the first suspicion fell on the measurements themselves. Rubin spent months checking calculations, re-examining the plates, and questioning the instruments before questioning the universe. That was ordinary scientific discipline. An unexpected bank statement is usually read twice before anyone accuses the bank. Extraordinary measurements received the same treatment. The graph refused to change. If gravity operated normally, and there was no evidence that it did otherwise, then something else had to be supplying additional mass. The visible stars, glowing clouds of gas and dust lanes, simply were not heavy enough to hold the outer regions together at those observed speeds. Without additional gravity, the galaxies should have begun flying apart. The plates showed they were not. One galaxy might have been dismissed as peculiar. Andromeda alone was not enough to overturn decades of accepted thinking. So the telescope returned to work. Another spiral galaxy, then another, and another. Each observing run produced new plates, new measurements, and another rotation curve. Different sizes, different luminosities, different positions across the sky. Yet when their velocity profiles appeared on graph paper, the same horizontal signature returned. The flat line was no longer confined to a single galaxy. Boxes filled with observations from galaxies, such as NGC 3672, NGC 7541, and NGC 2998, accumulated over years. Spread across a table, the rotation curves no longer looked like isolated curiosities. They looked like repeated versions of the same unexpected pattern. By then, repetition mattered more than surprise. Instrument errors rarely recur with such consistency across completely different targets. Random mistakes scatter in many directions. These measurements did not. Each additional galaxy removed another possible explanation. Earlier astronomers had already encountered hints of missing mass. Fritz Zwicky had reported that galaxy clusters appeared to contain far more matter than telescopes could see. Others had found similar discrepancies. Those observations remained controversial, partly because galaxy clusters are enormous, complicated systems where many explanations seemed possible. Rubin's measurements changed the scale of the problem. The contradiction was no longer hiding between distant galaxies. It was inside individual galaxies. The evidence also refused to remain confined to optical telescopes. Radio astronomers studying neutral hydrogen traced gas even farther beyond the visible edges of galaxies. Their measurements extended the rotation curves deeper into the darkness. The flat line appeared there as well. Different instruments, different wavelengths, the same result. By then, the question had changed. Scientists spent less time asking whether the anomaly existed, and more time asking what could produce it. Some researchers proposed changing gravity itself under extremely weak accelerations. Others argued for enormous halos of unseen matter surrounding every spiral galaxy. The debate became one of interpretation rather than observation, because the observations themselves had become increasingly difficult to dispute. The graphs did not change, regardless of which explanation anyone favored. Visible matter accounted for only a fraction of the gravity required. Roughly 5 to 10 times more mass appeared necessary to keep the outer stars in stable orbit than astronomers could account for through stars, gas, and dust alone. The simplest explanation was that most of the mass could not be seen. That conclusion continued to expand long after the original photographic plates had been filed away. Observations from X-ray astronomy, gravitational lensing, and later measurements of the cosmic microwave background all pointed toward the same picture. Modern cosmology now estimates that ordinary matter, the atoms making stars, planets, oceans, and people, accounts for only a small percentage of the universe's total contents. Far more exists in forms that neither emit nor reflect light. The physical identity of dark matter remains unknown. Its gravitational fingerprints do not. The final image is still remarkably simple. A rotation curve stretching across a sheet of graph paper. The line stays almost perfectly flat long after the visible galaxy fades from view. Decades later, that same line remains one of astronomy's clearest pieces of evidence that most of the universe cannot be seen.